Okay, I'm going to work on problem 8 of the Newton Laws practice problems that I sent out. So here is, in this problem we have a cup of coffee on a plane, and the plane starts to accelerate, not upwards, just it's staying at the same altitude. And we want to find out how fast, what the maximum acceleration of the plane is so that the cup doesn't slide backwards. Alright, so let's draw the free body diagram for the cup. If the cup is at the center of this axis on the right, then we can write down all the forces. First of all, there's the weight of the cup, which is downwards, and the weight, and then the normal force, which is upwards, because the cup is in contact with a surface. We're going to assume that the acceleration is to the left in the negative x direction. So that means that the force of friction will be to the right, and the force of the plane, or of the table on the cup, would be to the left. So let's label some of these. We have the normal force, the weight, the force of static friction, and the force by the table. Okay. The way we're going to approach this problem is to use Newton's second law, and we're going to treat the x and the y components of each force separately. So let's write down what we know about the x direction. In the x direction, there's only two forces with x components. That's the force by the table on the cup and the force of friction. So we can write down equations of motion in the x direction. So in the x direction, we have the x component of the force by the table plus the force of friction, the x component of the force of friction. Okay, and Newton's second law says that this should equal mass times the acceleration in the x direction, but we don't want the cup to accelerate. We want it to be stationary on the table. So this would mean that the sum of the forces in the x direction should equal 0. Okay, let's write down a similar equation for the y direction. In the y direction, we just have the y component of the normal force plus the y component of the weight. And again, this cup is not moving up or down, so we know its acceleration in the y direction is 0. And there we have two nice equations. So let's deal with the y equation first. We can solve for the y component of the normal force. It's just equal to minus the negative of the weight in the y direction. So the weight, the acceleration, the weight is mass times the acceleration due to gravity. So we have minus mg. And because the normal force is just upwards, there's no x component, this is actually equal to the magnitude of the normal force. Alright, we need this because in the x direction we have a static force, and we know that the maximum static force in the x direction is going to be, first of all, it's going to be positive because it's to the positive x direction, and it's equal to the coefficient of static friction times the magnitude of the normal force. So in the x direction, we have that the force due to the table is equal to the negative of the maximum static friction force in the x direction. And this is just minus mu s times the normal force, which we said was negative mg. So that's positive mg. Okay, now force is equal to mass times acceleration, so the force of the table is mass times the acceleration in the x direction. And look at this equation. Our masses cancel, and we have that the acceleration in the x direction is just the coefficient of static friction times the acceleration due to gravity. And we can plug in these numbers. We're given the coefficient of static friction is 0.3, and the acceleration due to gravity is negative 9.8 meters per second squared. And plugging these numbers in your calculator, we get 2.94 meters per second squared. Okay, in our problem, if we note, the only value we're given is the coefficient of friction, which is to 2 sig figs. So I'm going to write this answer to two significant figures, which is just 2.9 9 meters per second squared. Okay, that's it.